welcome to our second session of the day. This is our session on longevity. It's a little bit crazy as always, but that's just the way things work. So we have 4 speakers today, the first of which is João Pedro de Magalhães. I have worked for years to pronounce that name correctly, and João Pedro, I hope I finally got it right. João Pedro is a great friend of the longevity movement. He is a Portuguese microbiologist working in England at the University of Liverpool. His lab at the University of Liverpool studies aging through both computational and experimental approaches. His ultimate goal is to cure human aging, a wonderful thing. He'll be speaking to us today on the subject of aging and anti-aging, presenting a new paradigm for us. So without further ado, let me give the stage, or the screen rather, to João Pedro de Magalhães. Pedro de Magalhães.
Thank you. Thank you very much, Paul, for the kind introduction. Can you hear me well?
I can hear you on my phone, but I'm not sure the rest of the room can hear you. Oh, okay.
Yes.
Okay.
Well, thank you. Buenos días a todos y gracias a José. And I'm sorry I cannot be there in person. So let me share my screen. Okay, can you see my slides well? So, I'm a professor at the University of Liverpool, and I'm also CSO of a company, which I'll briefly mention today. And my goal is to give a brief overview of the latest developments in the longevity, aging, and also in the rejuvenation fields. So, I mean, as I'm sure you're aware, because of aging, we are all going to die within a relatively short time span from a, cosmological, civilization, even biological perspective. So, and that's something that's always troubled me. I'm aware that, that there's some people who can cope with it better than I can, but that's something that from a young age troubled me. And so ever since I was a child, I decided, and that's a photo of me doing my homework when I was a child. I decided that my career goal was to find a way of fixing aging, find a way of curing aging and reversing aging. That's what I wanted from a very early age. And I think that's for a transhumanistic perspective, that we want to enjoy the future. We want to live through the experiences of the future. Really, aging is the first hurdle or the first major limitation that we have to overcome. First biological limitation that we have to overcome in order really to live lives as I would like to, of exploring the stars and enjoying the fruits of technology in the future. So, okay, so that's always been my ultimate goal. But what have we advanced, and how much have we advanced in aging? Now, we know, and I'm sure most of you are aware of, that we can retard aging in animal models. There's a couple ways of doing this. It is possible to retard aging from dietary manipulations, the most famous of which is caloric restriction. I'm sure many of you are aware of. But if you restrict the amount of calories that animals eat, this is data from rodents, you can, while keeping minerals and vitamins healthy, you can extend lifespan, which is what you see here. On the right, you have a control group of animals fed ad libitum, means they can eat as much as they want, and you have a caloric restriction group that lives about 50% longer. It varies depending on strain. There's some caveats to this that I won't go into detail today, but you can retard aging with caloric restriction, at least in some species. From a genetic perspective, we also know that it is possible to retard aging. You can tweak genes in animal models like worms, flies, and mice, and you can extend lifespan. And I mean, the technology to change human genes is still not here. But if we could do that, and to quote Cynthia Kenyon, one of the pioneers in the genetics of aging, if we could change human genes, it could have a significant impact on aging. And again, it would retard aging. And we also know pharmacologically, there's a variety of longevity drugs that can retard aging in animals. Sure, you've heard of rapamycin, metformin, etc. So there's a variety of drugs that retard aging in animal models. And in fact, I mean, this is from an overview perspective I published earlier this year. You can, the number of longevity drugs that's been discovered is increasing exponentially. So this is from one of our databases called the Drug Age Database of Aging-Related Drugs. As you can see, the number of drugs associated with longevity is increasing exponentially. So there's a huge boom in the field of longevity pharmacology. There's a lot of drugs associated with longevity in animal models. I mean, I should say that the effects, the amount you can increase lifespan and you can retard aging with pharmacological approaches is not as great as with genetic approaches. So for a human translation perspective, that's an important caveat to keep in mind, because we cannot change human genes easily yet. So, and there's a couple of other limitations. I mean, one of them, of course, is that humans are not just big mice. There is a known gap in discoveries made in animal models and translations to human. I mean, I'm sure you're aware that cancer has been cured in mice lots of times. It doesn't mean it's been cured in humans. So just because something works in animal models does not mean it's going to work in humans. Now, my own perspective, particularly about longevity drugs, is that most of them will not work in humans, but I am optimistic that some of them will work in humans, and that this will allow us to have compounds that have longevity benefits in human beings. Now, again, the benefits may be relatively small compared to genetic manipulations. We're talking maybe 5-10%. That's still remarkable if you think about it from a medical perspective, but it's not really what we want. So there's this really big explosion, I think, in the longevity biotech industry. I'm sure you've heard of Calico, the Google company focusing on longevity. There's various companies, Unity Biotech, Jeff Bezos is one of the investors. So I definitely think longevity biotech has a very bright future ahead, with lots of companies, lots of great ideas, and lots of opportunities as well to make important discoveries and applications. And I'm sure you've seen about this news about this new company called Altos Labs, also from one of the investors being Jeff Bezos, that also, it's not official yet, but that will also be another big player in the field of longevity. So we have this big growth in longevity biotech, longevity drugs. We know of ways of retarding aging in animals. Having said that, longevity drugs and longevity biotech are not a cure for aging. I mean, even if these drugs work in human beings the way they work in animals, as well as they work in animals, we're still talking about an increase in lifespan, maybe 10, maybe maximum 15%. That means, yes, we're going to live longer, healthier lives, and that's fantastic, but we're not going to live forever. We are still going to die, and we're still going to face what, in my view as an atheist, is eternal oblivion, which is death. So that's something important to keep in mind. So on one hand, we have longevity drugs and longevity interventions, but these are just retarding the process of aging. They're not going to cure it. And therefore, I would argue that from a transhumanistic perspective, those are not enough. So what about rejuvenation technologies and rejuvenation biotech, which is something that's also been emerging? I guess the idea of rejuvenation is not new. I mean, back when I was a PhD student, and there's a photo of me as a PhD student, Michael Fussell and others argued that we would be able to reverse human aging using telomerase. So that was over 20 years ago. It makes me feel a bit old. And yes, I did think that hairstyle was cool at the time. So there was this notion that we would be able to rejuvenate humans with telomerase. So telomerase is this enzyme that elongates the telomeres. I'm sure most of you are familiar with it. And this idea and dates back over 20 years. Now, when you think about telomerase and telomeres, we know that telomerase is able to overcome senescence of human cells. So these are young cells, human cells, and these are senescent cells, okay? But if you activate telomerase, then you no longer have telomere erosion. So telomeres are the tips of the chromosomes. I mean, I'm sure many of you are aware, and they erode, they shorten with each cell division. And so when eventually they become very short and cells stop dividing. So if you activate telomerase, you overcome that. Yes, that's absolutely true. But of course, that's what happened in a Petri dish. And there's a big difference between what happens in a Petri dish with cells and what happens in an animal or what happens in a human being. So the past 20 years have shown that really no, telomerase is not a fountain of youth. In fact, if you have very long telomeres, that's not good for you either. So there's been epidemiological studies in human beings showing that it's like a Goldilocks zone for telomeres. You don't want your telomeres to be too short, but you don't want them to be too long either. There's kind of an optimum to it. So clearly, telomerase, may have some human applications, but it's not a way of rejuvenating human beings. Because again, what happens in Petri dish, what happens in a whole organism, they're very different things. So the other important thing to consider, I think sometimes when interpreting scientific discoveries and biomedical data, is that there could be important differences between short-term and long-term effects. So I'll give you one quick example. So this is growth hormone levels in human beings. So this is amount of growth hormone, and this is age, and as you can see, it declines with age. Growth hormone levels decline with age, and this is known for I think over 100 years. So we've known growth hormone levels decline, and so people hypothesize if that's the case, maybe if we increase the levels of growth hormone, that will have a rejuvenating effect, right? And we actually know that growth hormone treatments in older individuals can have short-term health benefits. They can increase muscle mass, they can improve the immune system, can improve libido, so they can have short-term effects. However, the problem is that they can have long-term detrimental effects. So we know, for example, from mice, that actually mice with lower levels of growth hormone, they tend to have longer lives. Why? Because growth hormone seems to, well, for one, it doesn't cause cancer, but if you have cancer, it makes cancer growth, because growth hormone, as the name implies, makes your cells divide and grow. And in fact, there's even some evidence that high levels of growth hormone accelerate mouse aging in the long term. So this is a good example, there's others, of interventions that may have short-term benefits, but long-term detrimental effects. And that's something to keep in mind. Again, if we want to intervene in aging, we want something that works in the long term. We don't want just something that works, for the short term. So, okay, so with those caveats in mind, there's another intervention, which I do think is an exciting new paradigm, which is cell reprogramming. So just as a reminder, so cell reprogramming was discovered by Yamanaka, who received the Nobel Prize. So basically, you can take somatic cells, so that's differentiated cells, a brain cell, a lung cell, a liver cell, and you can use these factors, these 4 transcription factors called Yamanaka factors, and you can revert, you can de-differentiate the cell, you can turn it into a pluripotent embryonic cell. Basically, that's what you can do. And now we also know that it is possible to employ cellular reprogramming to rejuvenate cells, at least some aspects of cellular biology, like epigenetic clocks, for example. So we know that if you have an old cell, an aged cell, that has some mitochondrial dysfunction, for example, and epigenetic marks of old age, you can use cell reprogramming, you can use these Yamanaka factors to rejuvenate the cell. And you can actually do it transiently. So you can do a short-term or partial reprogramming where you don't turn the cells into pluripotent cells. You can maintain cell differentiation, but you are rejuvenating the cells. At least as far as we can tell from some parameters. I mean, it's not 100% sure what is, how do we define the age of a cell? But for example, according to certain parameters like epigenetic clocks and epigenetic age and mitochondrial function, you can rejuvenate cells using these Yamanaka factors. And so that's quite exciting because that's, again, in vitro, it's a method of rejuvenation. So clearly in vitro, in cells, you can rejuvenate cells. Now, of course, the big question is this going to work in animals? Is this going to work in whole organisms? So that's the big question. I mean, you may have seen that this company from Jeff Bezos, Altos Labs, is going to be focusing on cell reprogramming for rejuvenation. So we will probably have an answer within the next years, I would say. So at the moment, there's relatively few studies in animals, in mice, using reprogramming. So we don't know yet whether cell reprogramming can rejuvenate organisms. We don't have an answer to that question. We know cell reprogramming, according to our current definitions of age, can rejuvenate cells in a petri dish. In a petri dish, it works. Whether it works in all organisms, we don't know. Maybe it will turn out to be, just like telomerase that works very well in a petri dish, but doesn't really work as well in whole organisms, or it may turn out to be something really revolutionary. So that's not something we can answer yet. No, I would say, if people, okay, Pedro, but tell us, what is your opinion? All right, I mean, take a guess. I mean, nobody knows. Maybe you're going to be wrong, but what's your opinion? My guess will be, I think that the most likely, but I could be wrong, I think the most likely scenario is that reprogramming will have applications in regenerative medicine. For example, people with spinal cord injuries. I mean, there's some data in mice from David Sinclair on eye regeneration. So I do think it's going to have applications for regeneration of particular tissues. Given that there is no evidence at the moment that it could rejuvenate a whole organism, I would say that's very unlikely. I wouldn't say it's impossible, but I would say that's unlikely. So we have these technologies for rejuvenation, and we have this emerging or potential technologies for rejuvenation. And I do think it's important we make the distinctions between them, because if what we want is to make people live a little longer, a little healthier, then yes, there's lots of longevity therapies, longevity drugs. There's a big field of longevity pharmacology, which is very exciting. And that's great. That's fantastic. I mean, I think we need this kind of interventions to preserve health and extend life. But that's not a cure for aging. That's potential interventions that will retard aging a little bit. The maximum you can do in animal models in mice is 50% increase in lifespan. And that's in particular types of mouse strains. It's not even in all mice. So I am optimistic about developing longevity drugs, but their effects are going to be relatively modest compared, I would say, with my ambition when I was a child, which was to cure aging. And I would hope that's the ambition of most transhumanists, which is to really overcome our biological limits and live indefinite lifespans. So on the other hand, we have potential applications of rejuvenation, which I would say is more risky. The chances of success are lower, but it could result in rejuvenation, an actual cure for aging. I think it's unlikely, but I wouldn't say it's impossible. And therefore, I think it's important, of course, that we also invest some time and effort in this kind of more riskier approaches. And I mean, I can tell you my lab, we're doing some work on cell reprogramming in the context of rejuvenation as well. And also in that context, I should mention that I briefly said at the beginning that I'm CSO of a company based in Zurich in Switzerland called Centaura. And our goal is quite ambitious, is to reverse aging, to develop the cell and gene therapies that allow us to reverse aging. So it's one of those examples, I think, of high risk, but also potentially high reward approaches that we need to overcome. And I've always said that I don't want to be, just counting the number of publications or grants that I get when I retire. I want to, at least try to make some important discoveries that allow us to ultimately cure aging, or at the very least have a significant impact on the human aging process. So with that said, let me briefly summarize. So I'm sure you're aware already that it is possible to retard aging in animal models in various ways: genetic manipulations, pharmacological manipulations, dietary manipulations. It is possible in animals to retard aging. It doesn't necessarily mean it's going to work in humans. That's still a big question mark. But clearly in animal models, there's loads of different ways of retarding aging, up to about 50%. That's kind of the maximum in mammalian models. Therefore, it's not unexpected that the longevity field is growing. I think it's fantastic to see there's more researchers, way more researchers than when I started. There's loads of companies. It's really an exciting time to be working in longevity field. It's really exploding. And my prediction is that most of these interventions in animal models will fail, but some of them will succeed. And I mean, even if we only have a few longevity drugs, for example, that will already have a significant impact on human health and longevity. That said, that impact from longevity intervention is merely not enough for what we want if we want to overcome death. And that's why we have, or it's also emerging, this concept of rejuvenation. It is much harder. As I mentioned, we know from in vitro studies that there are potential approaches to rejuvenation, like cell reprogramming, which I think is a very exciting approach that works in cells. Yes, cell reprogramming can rejuvenate cells, as far as we can tell, but still very big question marks about whether it will work in whole organisms. So it's a riskier, harder approach, but I could have greater benefits. Lastly, I've told you about our work with Centaura on developing technologies to reverse aging. So taking those high risk, high reward approaches. And really, I mean, I take it as a personal level as well, because I became interested in aging and working on aging because I don't want to die. That's really the reason. I never hid it from anyone. So we do need to take risks in the approaches we take, or we will all going to die. And personally, that's not something I want. And I think for most humanists, that's not something you want as well. So we really need to take these risks and try to develop these technologies. They could fail, but can also have a greater impact. And so with that, I think I'm out of time. This is way before, quite a long time ago, before the pandemic. Our lab, I didn't really tell you that much about the work we do in our lab, but this is our website, and feel free to drop me a line, and also invite you to have a look at the Centaura website. And again, feel free to drop me a line if any of this is of interest. Thank you very much for your time and attention. Muchas gracias, Jose.
Aubrey de Grey's prediction for longevity escape velocity is currently 2036, and that's a 50% chance of achieving LEV. What's your view on that date?
So I missed you there a little bit, but I know that the question, I heard you the last part about longevity escape velocity and its prospects in 2030. So that's 10 years from now. I don't think that's going to happen. I mean, if you look at, I think 10 years from now, it is possible to make good predictions in what's going to be available because we know what's being in clinical trials. So there's a lot of longevity drugs in clinical trials, yes. But their impact, even in animal models, is relatively modest. We talk 5-10% increase in lifespan. So you're not going to get to longevity escape velocity just with longevity drugs. So I would say that's unlikely. That would be my take. So unless something incredible could always occur, but I would say when you look at the rate of progress in preclinical models, there is rodent models, and what's been happening in clinical trials, and I mean, there's been quite a few failed clinical trials of longevity drugs recently as well, from Unity and Senolytics, for example. I don't think that's a likely outcome.
Okay. Hi. Okay. Excellent talk. I really valued your objectivity. There was no hyperbole. It was factual, and I think these are the type of presentations we need more of. So my question for you is, on one of your previous slides, you had a diagram, and you showed a chart versus, senescence versus non-senescence, severe epigenetic damage versus non-epigenetic damage, etc. It's about 4 slides back. My question for you is, there is a therapy you suggested, but you didn't identify it clearly. I don't believe it's growth hormone. It's something else that you said would reverse the aging. What is that? Again, it's on your slide. Go back. I think it's
This one?
further back. This slide right here, very important, and to me it's your consequential slide. So here you have somatic cell, and then going to IPCS. What is it in that somatic cell that would cause a cellular reprogramming? Thank you.
Thank you. Thank you for the questions. So this cellular reprogramming is done with 4 transcription factors called Yamanaka factors. So these are listed here, which is OCT4, SOX2, CLIF4, and c-Myc. So these are 4 transcription factors. And in cells, if you activate them, you can reprogram cells and you can rejuvenate cells. So in vitro, that's been shown. So yes, so that's called cell reprogramming, and that's one of the bases for the Jeff Bezos company, for example, is these methods for cell reprogramming using these transcription factors. But I should say, for example, first of all, as I mentioned in my talk, this works in cells in vitro. We don't know if it's going to work in vivo. And c-Myc, for example, it's an oncogene. It's a proto-oncogene, so it causes cancer. So whether you can rejuvenate cells without causing cancer, that's a big question mark still in a whole organism. But yeah, so this is called cell reprogramming with these transcription factors.
Okay, thank you so much, João Pedro. We are going to continue with the program, so we go back to our Master of Ceremony, to our moderator, Paul Spiegel. Thank you.
Thank you.